Thank you, Emil. So, welcome. A few of you that are here physically and the vast majority of you that are remotely participating. So I will try to talk a little bit about 6G and try to give a little bit of an answer to this question. What is 6G? Try to shed some light on that. And I will follow this structure to start with a little bit of driving forces, go through use case capabilities, and then come into technology. And towards the end, also talk a little bit about the timeline when we foresee this will happen, more from a standardization perspective. But just to set the scene, we're basically talking about something that will be deployed in 2030 and onwards. So it's not really 10 years from now, but almost. That's the kind of time perspective there. So let's look at some of the driving forces. What could drive the need for a future system? And we have identified 4 of these forces. First one being application demands. With that, we basically mean existing applications as well as new ones that we don't know about yet. What the needs they have in terms of data rates, latency, capacity, and so on. So they will, of course, push for more. Then we have trustworthiness, and that we see as something very, very important. If you're going to connect everything, the society will depend on this system. It needs to be trustworthy. And historically, I think cellular systems has been and still are very trustworthy. They have a lot of ciphering, encryption, and so on. But if we broaden the space that we try to cover with 6G, try to ground connectivity, also include compute and other things, we also need to broaden the concept of trustworthiness, that you should be able to trust that your data stays where they're supposed to, or that your compute and connectivity is always present, never fails, and so on. So it's a very broad thing, not just encryption. Third force we have here is sustainable world. And I think that goes without saying. The world is not sustainable the way we run it today, and we need to change that. And how can 6G and also 5G help with that? And the last one, it's called Simplified Life here on the slide. Maybe not the best title, but its intention is to capture the distributed AI that we will see. We already today see a lot of artificial intelligence and machine learning and things like that running and helping us to do different tasks in society. That will become more and more common in the future, and these AI machines need to talk to each other. And they will have demands, of course, in terms of data rate, but that will end up under the blue bubble, but also other demands. What type of data formats do they exchange information with? How do you build a distributed AI machine, and so on? That will be the fourth driver. So these are the 4 things that I've seen that come from the outside perspective that could drive the need for something new. And then use cases. And when I talk use cases, I usually say that whatever I say is probably dead wrong, because it's extremely difficult to predict use cases in detail. I mean, remember the 3D killer use case, that's our video telephony. No one did that, but it happened later on with iPhone and Androids and so on. So it's very difficult to pinpoint a single specific use case. But so I just brought in this slide, trying to illustrate a little bit what we have in mind. And it is a lot about bridging this digital world and the physical world. So we have the physical world where we live, even though it's been a lot of digital the last 2 years. The physical world where things happen, we have sensors, we collect information, we affect things. And we have a digital world with a digital twin, very detailed model of that physical world, where we can do experiments, we can try out new things, try to figure out what to do, and then feed back that information to the digital world. So it's a lot about moving back and forth between these different worlds. So we have connected intelligent machines, for example, machines that connect and do things together. Could be robots, or could be a robot and a human to work together on a task or something like that. Internet of senses. In some sense, that's just an extension of what we have done in the past. I mean, the first telephony 1G, that was really remote audio, that you can hear things. Later on, we added video, but why should we stop there? Why not continue with touch and smell and a lot of other things? And this digitalized and programmer world, that's a lot about going back and forth between these 2 domains. And of course, we should do this in a sustainable way. So actually, we will save my reputation of predicting the wrong thing by not going into details on use cases. we can try to do that. We can have a chat on that afterwards if you're interested. But I'll just leave it here also from the interest of saving some time. And the next step, when we know a little bit about use cases, or at least what type of use cases we'll have, what capabilities do we need? So let's start with what I call the classical capabilities in this blue circle. For example, have achievable data rates. Of course, we want higher data rates. We would like to transfer information faster in the future. We should be a little bit careful, though. We should not talk so much about peak rates. There's a tendency a lot of times to end up with a peak rate discussion, but the peak rate is quite irrelevant. What really matters is the achievable data rate. What data rate do we actually get in reality? But we want higher achievable data rates. Same thing with latency. Of course, we would like to push down latency. In 5G, we talk a lot about 1 millisecond end-to-end latency. There are cases when you wanted to push that further down, but probably more important is to have reduced jitter. Many applications run just fine with 1, 2, 3 milliseconds, but they depend on very low jitter. So it's probably more important to enhance in that domain than in the absolute lowest number. Positioning that we've had for a long time, and that's something important, being able to position things where they are. Traffic capacity, another classical metric, have been with us since the 1G. We always need more capacity because people use the system more and more. And you can find in there some mobility reports how the traffic need is increasing. We need to meet that with more capacity. Coverage, of course, if you don't have coverage, you don't care about the rest of the metrics because then you don't have a connectivity. So coverage is also very important. And really, truly global coverage everywhere would be nice to get. And network energy efficiency. Our systems need to be sustainable and cost efficient. And for that, they need, among other things, be very efficient with energies. We need to push that down. But all this is in some sense classical capabilities that we talked about also in the previous Gs. They continue to be important. But we should not view 60 just as 5G times some factor of X. We should not just scale up 5G, we should do something more. So we actually have an outer ring of, I call it new capabilities. You can of course discuss what's new, what's classical, and the border between the two circles is a little bit blurry. But trying to address new capabilities for new use cases. Security and privacy, that goes back to trustworthiness in a wider sense, not just for connectivity, but for everything. Service availability, trying to do, the service of course needs to be available there. I need to trust that my service is up and running. Even if someone accidentally cuts off the cable to the base station or something happens, then you still would like to run your service at least to some extent. For example, if you have connected your factory with 6G and suddenly there's some excavator out in the street that cuts a cable, you don't want your factory to stop. It still needs to operate and continue to function. Service versatility, you would like to be able to deploy a lot of different types of services in a flexible way and scale them up and down. Dependable compute. With that, we tried to address the fact that 60 is more than just communication, it's also compute. And some of that compute task they may execute in the device. Some of it may execute in the central cloud and some of it in the edge cloud. And depending on where you are and what needs you have, this compute task may move between these different places in the network. And to do so, you of course need interfaces and APIs and mechanisms to be able to move that compute task back and forth. That's one example we need to do there. Deployment flexibility, I think it speaks for itself. We want to be flexible in our deployments, run in different types of spectrum allocations, be able to set up networks temporarily if you have a rock concert or disaster zone or whatever. Sensing, that's an example of a new capability that in some sense is an extension of our positioning. But really what we have in mind here is that if we anyway deploy a large number of base stations and other nodes for communication purposes, can we reuse that infrastructure also to sense things, sense the surroundings? A little bit like a radar, for example, try to build up a map of what's around us. If we can do so, which we can, and have requirements of that, then we can feed that information into the digital twin and know more about what's going on and build up a more detailed twin. And the last example of a new capability is extreme devices, in particular for very low-end IoT applications. There are a lot of applications where you really want a super low cost of your device, very low power consumption, way below what we can do today with today's IoT standards. So that's one example of an extreme device. And then last but not least, we should not forget cost efficiency and sustainable. It needs to be sustainable, both from a cost perspective, but also in general to be friendly to the planet. And as an engineer, of course, you can come up with a lot of cool technology and fancy MIMO schemes and whatnot. But if the cost of those new schemes, new things, is too high compared to the benefits they bring, they won't happen. Even if it's fun with technology, and it truly is, you should keep this cost and sustainability in mind as well, so that it really can happen in reality. So that's a little bit about capabilities. And the bottom line here is that 6G is not just a scaled up 5G, it's something more, it's broader. So it needs to have broader capabilities and also covers more than just what 5G covered. And then technology. We have, I grouped on the slide, I grouped it into 4 areas. Oh, I thought I took away the animations. Okay. First one being limitless connectivity. So that all types of technology that can help us with getting a truly limitless connectivity. The vision here is that no matter where you are and what you want to do, connectivity should not prevent you from doing what you want to do. If you have a certain application, certain task, you want to do something and you need a megabit for that, then you should get a megabit. If you need a gigabit, then you should get a gigabit, and so on. The connectivity should always be there. The connectivity should not stop you from doing what you want to do. That's the division. And then we have a bunch of technology groups here, subgroups and technologies that will help us in that. We'll get back to some of these in coming slides. We also have trustworthy systems. And that goes back to this trustworthiness we talked about in the beginning. And it's, as I said, a broad range. It's not just for the communication part, it's also for the compute part. How do you run this kind of trusted enclaves in the cloud so that your information doesn't leak to someone else with all of these aspects? How do you trust that that's the one you're talking to is the right one? So you need some trust certification mechanism and so on. So everything that still has to do with trust. We have an area that we call cognitive networks. Also that one's divided into a number of smaller sub-areas. But with cognitive networks, we really mean the idea of using AI and machine learning inside the network to optimize how you run the network, both the communication part, but also the compute part of it. So ideally, what you should be able to do is to have some kind of intent-based configuration of your system. You should be able to tell your system that I would like to set up an IoT service that should have this data rate, and it should not affect my existing MBB service, for example. And then the cognitive system should be able to figure out how to configure all the parameters, how to set up the system to run this new service, should learn from what's going on, the data that's flowing through the system, there's compute and all the processing that takes place, and readjust parameters and optimize as we go. And also be able to explain to me as an operator that I took this and this and this action because of. So that you can really configure the system in a high level manner. Just tell the intent to the system comes back and say, yes, I did this and this and this because of. That's the idea. And use a lot of AI inside the system and data-driven operation and things like that. And the last area is network compute fabric. I think maybe it's been obvious from what I've said so far and from what I heard elsewhere. But we really see that communication and compute is going together and kind of mixing. So we will be running parts of our communication networks on cloud. And if that same cloud is also running some other applications, then we have this kind of unified communication and compute infrastructure. And that we collected here on the network compute fabric. So there's a lot of tools, how we can unify these two worlds and what mechanisms we need to make that happen. That's kind of 4 major areas of technology that we have in mind for 6G. And then, of course, as I said, within each of these boxes, there's a lot of things to do and think about. So I will just have a few examples on this first in a few slides. Because what we try to get to is some form of intelligent network platform. We have all the so to say, classical networks, cellular networks at the bottom. They will evolve, of course, better and better with 6G. And we have some form of platform that can integrate these different networks, maybe add some value-added functions, and provide a unified API, unified interface up to the application developers. So they don't need to bother with each individual network. Because if you develop an application, you just would like to focus on that application, develop it once, and it should run everywhere, no matter of the details on the communication network. So that is a little bit what I try to illustrate in this middle platform here. But this is something we don't have today, I would say. But you could, of course, plug in 5G and 4G under here as well. So it's a kind of gradual path into that domain. And then on top of that, you can deploy all your application, whatever that is. Maybe these examples here are a little bit 5G-ish, but nevertheless, if you come up with something new here, just put it up there. So that's a little bit the vision about the platform, that you should be able to come up with one platform that supports your application everywhere, no matter where you are. Okay, let's jump a little bit into technology. And here's just a few examples of technology components. I will get back to most of them in the coming slides, so I won't spend more time on this slide. To start on the, I call it the network adaptability, but it has really to do with these cloud native things. So what we see, as I said, we see that a lot of communication, they should be able to exploit and benefit from the cloud, the general compute cloud stuff we have today. All those tools we have, fully service-based. That has to do, for those of you that are a little bit more into the details on 5G, you may know that the 5G core is more of a service-based architecture. So basically, instead of having nodes talking to each other, you have functionality that pretty much any functionality in the core can talk to any other functionality. So we did that in the 5G core, but we haven't done it on the RAN side. But we see parts of that will come down to RAN as well. And then I have two bullets on function separation and the simplification. And that really has to do with the fact that this is a very complex machinery. We should be careful here to make sure that it doesn't get overly complex. So we should really think through what kind of interfaces do we need to standardize in order to get interoperability, obviously between the handset and the base station. But maybe we shouldn't try to decompose and chop up all the different pieces inside the network in very, very small units and standardize them, because then it will take a very long time, be very complex. So try to keep it simple as well. Programmable devices and network, that also relates back a little bit to this use of AI inside the networks. But a few examples of what one could do here and what we want to do is to be able to deploy new functionality in the network without having to go through the standardization process, which obviously takes some time. So a little bit more of this DevOps-like style that you run on the IT industry, to try to bring that more into the compute side as well. And one way of doing that is to have the network and the devices more programmable. So you can think of about training an AI model on the network side with all the compute facilities you have and all access to all the information you have. Once you have trained it, you can download it into the device and execute it in the device. So for example, if you come up with some new handover mechanism that you think is much better in your deployment, you have trained that to develop that, you can download that in the device, and the device can execute parts of that handover procedure in a new way, instead of having to go through standardization and then come up with something new there, which takes time. And then flexible and dynamic networks. For example, we integrate new tier types of access nodes. So you see a small satellites in the illustration there, for example. So how can we include satellites into this overall network as a complement? Because if you're serious about having a truly global coverage, there are places on Earth where it's difficult to put up a base station, even if we would like to do so. Oceans, for example. So satellites could be a complement in some areas. And how do we integrate that and how do we interact with that into the network? These are a couple of things what you have in mind on the more on the architecture side, so to say. Then if we jump into radio, spectrum. Spectrum is really essential. We can't do much radio communication without spectrum. And what we say about 60 is that it should cover wide range of spectrum from sub-gigahertz up to what we can call sub-terahertz. So it's even wider than 5G. That said, not all parts of this frequency axis are equally important. These lower frequencies here, 1, 2, 3, 4 gigahertz, they will remain extremely important also in the 60 era, as they are good for providing coverage. It's very difficult to provide wide area coverage if you go up to several hundred gigahertz, because the radio propagation is very tough up there. So for coverage reasons, you still need to use these lower frequency bands. And that's fine. The aspect one need to take into account, though, is that there is already cellular networks running in this frequency range, 4G and 5G, for example, and they won't disappear overnight. So if an operator would like to introduce 60, it needs to be introduced in what I call the spectrum compatible way. You need to have a 60 that in one way or another is able to operate on top of a 5G and a 4G carrier. We actually did that when we introduced 5G. We had a mechanism so that the 5G carrier can be put on top of a 4G carrier and they kind of can coexist. I think we can do it even better than what we did in the 5G case. So let's try to do that in 60 by learning from what we did in 5G. And that would allow an operator to gradually introduce 60 in this lower spectrum where they already have 4G and 5G running. So a very important piece of spectrum, and very important that we can introduce it in a smooth way. Another range that is interesting, of course, between these two red boxes is already relevant, but the 7 to 24 gigahertz range. We see today NR is going up to 6 at least. Fundamental is nothing in the technology that would stop us to go higher in this low half of the spectrum. But the 7 to 24 gigahertz range is currently not used by 5G. And it's a very nice frequency range. It's low enough to give decent coverage. So of course it would be nice to run 60 in this range as well. However, there is a couple of other users of this spectrum at the moment. It's radio links, it's some satellite communications and so on. So to get access to this spectrum, we probably need to think how can we coexist and how can we share it with those existing services in a smooth way. And then we have 30 gigahertz and a bit upwards, the millimeter wave range that was pioneered by 5G. That will remain important also in the 60, so that will be there. But then basically a comment on the sub-terahertz range, because quite often, if you go to a 60 conference, you hear a lot of people talking about the terahertz frequencies or the sub-terahertz frequencies. And yes, it's a new frequency. It's of course very challenging and interesting from an engineering perspective. It's quite tough to build RF components up there. They're not as mature as they are further down. However, the propagation conditions up here is also very challenging. You will not be able to go around corners. You will have difficulties going through a window and so on. So these very high frequencies, they can offer a lot of bandwidth. They can provide high data rates, but only in very specific scenarios. So I think they will be more for kind of niche applications. The important range is still this lower range, the 7 to 24 and the millimeter wave range. The terahertz range is more for niche applications. But 60 as such, we will support all these frequencies, not just the red ones that I highlighted here. Then one of the other technologies that I had on one of the earlier slides, that was what we call the zero energy devices. And that's just an example of a device that you don't have to replace the battery in. So it's kind of a battery-less from an end user perspective. You just deploy it, it does what it's supposed to do. You don't have to go there to change the battery or to charge the battery. It can harvest energy from some other sources. Could be temperature gradients, could be vibrations, solar power, in some cases even the RF waves themselves. So no need to change battery. And that's of course quite attractive if you think about some sensors or something like that, that you can just put out and forget about them. They just sit there and do whatever they need to do, collect temperature information or whatever you want to sense and feed that back. So this is a type of devices that is much more extreme than the current IoT devices in cellular networks, the narrowband IoT and LTM. Because this is very, very, as you see in the figure, very low down in the power consumption and complexity scale. But this makes them quite challenging to design, because with this tiny, tiny amount of energy you have available, what kind of physical layer should they have? How should you do mobility? How should you do security and ciphering, encryption, and things like that? We need to rethink a lot about the radio and the protocols here if you're going to support these zero energy devices. So this is quite an interesting area, actually. And you can also envision that in the long run, maybe we can combine this with printable electronics. You can just print your 60 low-end device on a piece of paper, put somewhere, maybe on a milk carton or milk box or whatever, just to track the temperature in the food industry and things like that, asset tracking in the factory hall and things like that. So in principle, you can replace barcodes, which I use today, with this. But the barcodes you need to see to be able to scan. With this, you can basically have a pile of boxes on the floor, and you can read each individual box and see what it is, and maybe even the temperature inside that box, or whatever you want to read. So that's the type of vision here. But that will require some new radio access work as well. Another new area would be joint communication and sensing. If you anyway deploy communication infrastructure for communication purposes, why not try to use it also for sensing purposes? So that we can try to sense the surroundings, collect information of what's going on around us, and so on. And that the information that we collect could be different types. It could, for example, be if you have anything that affects the radio waves, basically. So, I mean, we have already shown from an Ericsson perspective that you can actually see whether you have low rain on a very local scale or not by just looking at the signal strength on microwave links. That's, of course, very useful input to weather forecasting services. But you can do more. You can use them as some kind of a radar type of setup, so that maybe you can track cars that are moving around. You can see whether the room is empty or full of people. You can actually, in some scenarios, see whether the heart is beating or not on a person by just monitoring what's going on with the radio waves and so on. So the challenge here is, of course, a little bit to see what type of things can be sensed, and what of these things we can sense make sense to sense, so to say, and that can be useful in reality. But I think one should keep in mind that because sometimes you see that people say, yes, let's go up in the terahertz range, we get an excellent radar. Probably true, but you don't get excellent communication, and then you kind of lose this joint communication and sensing. So I think, at least the way I look up on this is that we start from a communication perspective, and then we try to expand into the sensing and try to reuse our communication equipment also for sensing. And that fact will mean that we need to also handle the frequency ranges that are actually used for communication, also the type of infrastructure we put out there for communication when it comes to requirements on power amplifiers and things like that. So it's really joint communication and sensing, because then we can get the sensing halfway for free compared to building a separate sensing network where you have to pay for that network in itself. And at the beginning, I promised a little bit on the timeline. When will this happen? And this is a timeline from a standardization perspective. We're in the beginning of 2022 today. And we predict, not just we, it seems to be quite a wide industry consensus on this timeline, that in 24-25, there will be discussions in 3GPP on requirements for 6G. What should the 6G system be able to do? What type of data rates, what sensing accuracy, etc., etc. And then once that is done in 25, 26 and up to 28 or so, there will be the actual standardization work to come up with the first standard for 60 that hopefully is ready in 28. You'll probably see some early commercial deployments in the 28 timeframe, a little bit on a wider scale in 2030 or so. So that's the timeline we see. And that means that we have roughly 2 years from now until we start to discuss requirements in 3GPP, and maybe 3 years before we start to discuss technology. So we're still a little bit in the research phase for 16, but it's not so that it's a huge amount of time. It's a couple of years before we start to see this happen in standards. And then we have the whole standard procedure to run through, of course. That takes another couple of years. But that's a little bit how we see it on the standard perspective. That actually brings me to the last slide, a little bit ahead of schedule perhaps, but since we didn't have questions during the presentation, might be good to have some time at the end. We talked about when, this is the 2030 timeframe we're talking about. We said that 60 is more than just communication, not just a scaled up 5G system. It's more, it includes the compute. It's really a platform that provides this trusted, ever-present communication. That also was seen in the capabilities we talked about, that we had these two circles. When I said the outer circle are new capabilities that I haven't really talked about in previous Gs, but will become very important in 60 era. And then I mentioned a few examples on technology components on the radio side. It was not the complete list. There's a lot more than what I had on the slides here. But just to give you a little bit of flavor for some of the new things, I took a couple of examples. So with that, I stop, and I guess we have plenty of time for questions, at least 20 minutes or so.